Good morning to all. Now we will have a very lecture presented by Professor Miguel Alario Franco from Madrid, from the University of Complutense in Madrid. This lecture is sponsored by Laser Line Scanning, which is a company dedicated to enable large area laser processing. And Professor Alario, whom I met a few years ago.
Many years ago.
At the Boston EMRS, maybe 1987 or so. At that time he was presenting work that he did in collaboration with CNRS, the Laboratorio of Crystallography in Grenoble, in France, where they deciphered what the arrangement of oxygen in 1, 2, 3 eco material was. This is a very important contribution. And he has been a leading figure in the study of perovskites and in general in solid-state chemistry. And I would like to welcome him here to give a lecture on the surprises in the high-pressure synthesis of high-temperature superconducting cuprate materials, substitutions in ruthenium, strontium, rare earth cuprates, lanthanide contraction, redox behavior, and order disorder. Please.
All this. In fact, well, good morning. First of all, I would like to thank the people that has made possible my visit to this fantastic place and this most interesting meeting, Professor Genser and Dr. Germán de la Fuente and Dr. Javier Campo. And of course, I thank you for staying here early on a Sunday. In fact, when I was a boy in Spain, in Madrid, the only important thing we did on Sunday was going to the Mass. So it's the first time we have a different kind of Mass in here. I'm going to talk about things related to high pressure and synthesis of cuprates. So I'm an experimental solid-state chemist, and we have been doing for a long time synthesis of different superconductors, and then we have analyzed them. We have done synthesis at room and at high pressure. Today we'll talk about the high pressure materials. And then we have characterized them by electron microscopy. These are the two techniques that I developed in Madrid along my career. So we set up an electron microscopy center and a high pressure laboratory. And part of, most of what I'm going to say came thanks to this thing. So the talk is divided into two parts, and when I say that, it's really divided because for technical problems I haven't been able to put them together, even if Javier Campo helped me to try. And then so I will do the first half, and then I will switch over to the second one, and I hope there will be not too much of a problem. So first I talk about the problem with the lanthanide contraction, which I will explain in just a minute, and secondly we'll see the influence of size, which is what we could expect from the beginning. So the two together, I expect, will give you an idea of what is the problem of making, of fabricating this material. So we are going to No, strange. Well, it doesn't work here. No? Perhaps. Yeah. Yeah. Okay. So first, pressure. What is pressure? Pressure is the force per unit area perpendicular direction to the object, but there are many types of pressure. So perhaps we can have a look to how many types of pressure there are: physical, demographic, political, military, arterial, ocular, intracranial, atmospheric, pneumatic, hydrostatic, internal, external, saturated, vapor, partial, etc. Mechanical and chemical, which is the one more relevant for today, And then we also have a different intellectual pressure, which is the pressure that makes the media, the press, the radio, TV, and today we also have the pressure groups, which are the various part of the social network. So in fact we are totally surrounded by pressure from all these points of view. And the materials I'm dealing with are the metal cuprates based on ruthenium, and these are interesting materials for a couple of reasons. This derived from YBCO when you replace the copper in the charged reservoir layer by ruthenium. That's a family that was found years ago, and we have been working, several groups have been working on this. The characteristic is that if you do the magnetic measurements, you get first a magnetic peak, following a superconducting peak. And in fact, if you remember, Ginsburg suggested years ago that there was incompatibility between magnetism and superconductivity, but in fact here it's not incompatible because they are not the same electrons which do the one thing or the other, but the superconductivity is of course in the superconducting planes that we will see from time to time in the talk, and then the magnetism is in the octahedron, the charged reservoir layer that now is made by octahedron. So in fact this is so-called a superconducting magnet and not a ferromagnet superconducting ferromagnet. So the interest of this material suggested to us to make the whole family, so using all the rare earths instead of gadolinium. So and before that, we'll have a look to the atom's size, because size is a very common concept in solid-state chemistry, in synthesis of material. This is the transition metals metallic radii, and you see that they make an interesting bend curve here. This is due to the increase in the charge when you go to escalate the atomic number, but then you also have the electronic repulsion between the electrons, and then that makes a decrease and increase. So in fact we don't have a straight line, not a linear relation but a bent one. In fact this was already apparent, so there is a minimum equilibrium between the two. In fact that was already visible in the one of the earliest periodic tables. This is a modern version of Lothar-Meyer, which was in 1862, and if you see the atomic volumes here, well, you see that the transition metals here and here, but we have this part in here which is a little special. These are the volumes, but in fact, if you do that with the atoms, we can see the periodicity, of course, when you look at the atomic radii as a function of the atomic number, and then you have here, that's the groups, which are periodic, and the periods, which are also periodic. And then we have the three transition metals, 3D, 4D, 5D, which are these bent. But then we have the lanthanide contraction. As you can see that this is totally different, and then we are doing the same thing. We are soi-disant filling the F electrons, but the F orbitals are slightly different, and so we observe, instead of this variation, we have a kind of decreasing plot, and this is the lanthanide contraction is observed when you increase the atomic number, and you go from 1.106 for the lanthanum to 0.8 for lutetium. In fact, there is something in the middle for gadolinium because it's a F7 configuration, and that makes a little extra stability. So this is the lanthanide contraction is usually explained by this equilibrium between the increase in the charge due to the increase in the protons in the nuclei plus the electrons repulsion in the atoms. So we have this in this case. The F electrons are not very much screeners, and then so you do not, the contribution of the repulsion is not sufficient, so you really get a decrease. So the charge is really the main culprit of the evolution of this size of the lanthanides. So what is the problem? So it was known in the literature that if you like to prepare these materials, all the family of the ruthenides, with all the rare earths, then you at room pressure you can prepare samarium, europium and gadolinium, which is this way, just in the middle. So we were surprised and interested in see what happened in here and what is the reason why you cannot really get at room pressure the same. But we have a high pressure lab, so we decided to do some substitutions in this material. First of all, substitute the rare earth, then ruthenium by chromium and ruthenium by iridium. So, and to see what happens in this substitution, whether we'll be able to do that at room pressure or what was going on. And in fact, so for the room pressure, you have this typical synthesis where you get first the double perovskite and then you get the material. But for the high pressure ones, you'd have to use a different way, a different reaction. Otherwise, when you increase the pressure, the double perovskite is more stable, so you cannot really make it. So that was the other, these were the two reactions for the synthesis. And then it's important to say that often in high pressure synthesis of materials you get some secondary phases. They are not really impurities in the sense that an impurity will be in the same material, some replacements of atoms, but these impurities or these secondary phases rather do not really invalidate the conclusions, I believe. So we'll go on to knowing that there are some secondary phases. Well, these experiments were done in this bell type, which is one of the press that we have in Madrid, and so you have to heat the sample at the same time that you do pressure, which is a rather tricky thing, and then you have to cool the chamber in which the reaction takes place, otherwise the whole thing will broke. So, in fact, with these things, you have to use a crucible, which is normally gold or platinum. You can sometimes use other metals, and then you set up this kind of system where you have a graphite furnace, which is a cylinder there, and then you put two tops, magnesium oxides, and so you put this is the bottom piston, and then you put that inside in this chamber, which is the one that is cooled, and then in fact, that's the real cell. Inside this will be about 3 to 5 millimeters, 3 by 6 millimeters, I think. And so you fill the sample, you put that, you increase the pressure, and when this is at high pressure, you increase the temperature, and then you quench the temperature and put the pressure slowly down, because otherwise the pistons, which are tungsten carbide, will break. This is very... So it's a tricky experiment. An experiment lasts for about 2 hours. Once you start to put the sample and so, in standard 2 to 3 hours. Yes. So for the standard one, the ones that you can make at room pressure, this is the diffraction pattern. These are triple perovskite, as the unit said, and these are some of the secondary phases. So it's difficult. The more cations you put into the cell, the more secondary phases you get. It's difficult in these conditions where you compress the atoms that you really get a fast kinetics. You should wait perhaps too long or increase the temperature. So these are the secondary phases. So these also are metastable phases. So if you leave them at room pressure, well, it's not very clearly here, but after time they decompose and they do this, the double perovskite. You see here the double perovskite is appearing with time. So they are really metastable phases that you can actually obtain at high pressure, but they are unstable, they are metastable, and so they will end up by decomposing into the original materials. Now, this is simply at room pressure and room temperature, and that's the decomposition, so metastability. So then we found an interesting business, which is what I'm going to describe now, which is that the optimum pressure, which I'm going to find for the synthesis of these members, was not following the lanthanide contraction. So we found what I call a first surprise, and this first surprise is that the optimum pressure to prepare these materials for the different areas was, as I say, not a straight line here, but it was a Gaussian, you see. So that means a couple of things. At room pressure, you can make these strings, those in the middle of the plot, and then the medium cations. For the small cations and for the high cations, big cations, you need high pressure. And in fact, the optimum pressure is that if you do not use high enough pressure, the phase doesn't form. And if you use too much pressure, it decomposes. So we are in a narrow window, and this narrow window, which is not precise, it's not like the melting point of water, it's a window, is where you can actually prepare the material. And, well, it was the work of Rocío Bustos, Antonio Fernández Santos, Antonio dos Santos. So that is a surprise, the fact of getting, instead of a lanthanide contraction derived, a Gaussian relation. Then this is, and you see here what I mean by optimum. In here, at 40 you get a little bit, at 60 increasing, and then the original phase decreases, and then, so this is what actually we observed and make us to call this window to prepare to define these materials. So before describing the whole thing, we characterize these phases by high-resolution electron microscopy, and they are perfectly normal, so they just like one expected. This is the phase with praseodymium, and this one is with dysprosium, and you can actually see that there is nothing special. So they are normal phases. The only thing is you have to prepare them under those circumstances. And that's the structure that Paul Hadfield determined years ago. There are interesting things in the splitting of subatomic positions. I may talk about that later on if I have time. So the magnetic properties is interesting. This one is not superconducting, but you can see the magnetic peak, depending, of course, on the field you apply. So, in fact, although some of them are superconducting, some not, they are all magnetic, and the unit cell volumes of these phases rarely follow the lanthanide contraction. This may seem a contradiction, but in fact it is not. Is that the lanthanide contraction applies to the thermodynamic properties, and the unit cell volume or the energy, the lattice energy, they are thermodynamic magnitudes, and they follow. So the unit cell volumes follow the lanthanide contraction because this is a thermodynamic property of the thing. And then the phases that we obtained were these. In fact, we prepared 12 different phases with all the rare areas. Those with points is just a small, less than 50%, more than 50%, this one, the majority. We could make them more rich, but it would be time-consuming and more expensive, so it wasn't running. And in the same way, we arrived to the maximum in the family that was obtained with the yttrium, and it's about 50 Kelvin. So that's an interesting thing. So we have a new family of materials, or rather, we made all the materials of the family, some of them were known, and we have this particularity that I have already mentioned. Second thing is we prepared another family that replacing, instead of always with all the rare earths, replacing the ruthenium by chromium. Chromium is a very interesting material for its oxide, and then we found there a second surprise. The second surprise is that you have more or less the same thing, a Gaussian. This is a flatter, much flatter Gaussian, and this is, so you have the medium metals in here, and then again, for that and for that you have to increase the pressure. And the interesting point is that there is a difference of 60 kilobars between this plot and this plot. And this is well tribute to the fact that RuO2 is a stable oxide, while CrO2 is not. CrO2 decomposes at relatively low temperature, so the difference in stability between ReO2 and CrO2 makes the plot to displace in that direction. So we carried on. The crystallographic data again follow the contraction, as I said, and then this kind of thing is normal. Then the magnetic susceptibility here, we see the magnetic peak when the rare earth is not magnetic and they suppress when it is magnetic, so it's relatively simple, the interpretation of the results. So they are, let's say, normal materials. It's only the problem of the synthesis. The chromium materials are not superconducting. We did not expect them to be, but still, you always have to try. And then they are magnetic, as I said, in one case, and non-magnetic in the other, depending on the rare earth. Then, in the case of the last substitution, was ruthenium by iridium, and then, once again, you see that increasing the pressure to that window, you obtain more and more of the material, and so we got this other family is here. Here we have a difficulty is that the maximum pressure in our lab is this one, so two more phases were obtained in Vienna by Professor Huber. But in fact we get another Gaussian, and at the end what we have in the whole thing is always a Gaussian, provided that we use the whole family of rare. Again, the crystal structure was expected for the material. We observed a relatively novel thing, which is that it's a triple perovskite, and the triple axis is sometimes oriented in one direction, sometimes in the other direction, and sometimes in the perpendicular direction. So this can be observed in the electron diffraction patterns by the extra spots. And then we have a model for this of microdomain texture, where the domains are, the z-axis is oriented in the three space directions. There is a problem here with the domain walls. Well, we have a model that we haven't really go too much in deep. But as I said before, the fact that these positions are split means that the octahedra can be inclined, so this facilitates the connection between the microdomain walls. Then, these are the magnetic properties of the iridates that are not, also they are not superconducting, but they have very interesting magnetic properties, red glass, antiferromagnet, and so on. So the conclusion from this part is that we can prepare, in fact, a big number of phases, 30 in all, which are related to the ruthenate ruthenocuprate, and these all have this characteristic of a Gaussian plot for the optimum pressure. So that's a resume of what we have obtained. So the next point is, what is the origin of the Gaussian section? The optimum pressure is the ionic radii. And then you have to think first of all in the structure, because if you look at the unit cell of IPCO in this situation, then we have a so-called hydrostatic situation, because you apply the pressure, and in fact, and then we only apply in the vertical direction, but as we have the chamber, in fact, it's hydrostatic. So what that means is the rare earth, which is probably responsible for the problem. It's the rare earth what we are changing, actually. So we thought that perhaps that was related to here. And the explanation that we found, I start by very low chemistry ideas that you will know is that in a chemical reaction you have always an initial state and a final state, but you have to go through an activated state in general. If you put hydrogen and oxygen in a flask, it will never react unless you put a spark. Well, this is a general thing, and in fact there are two aspects here, and I apologize for being so elemental. in this description. So you have this part, which is the free energy thermodynamic, which is lanthanide contraction, and then we have this other part, which is the activation energy. So in fact, what we believe we are observing is a kinetic problem, a problem in the starting of the reaction. And then this is the activation energy, where we observe the Gaussian relation. So then, what is happening along the rare earth is that we are adding F electrons, and so there are 14 F electrons. So this is the period. These are the different configurations, and then I'm going to show you a cartoon of the F orbitals, which are seven F orbitals. And in fact, well, this is just a cartoon. The orbitals are not moving. It's just a representation. You know very well that is the square of the amplitude and the fraction and so on. But at the end of the day, you have all these things together. And if you are putting electrons there, as we say that they are not very much screening, so there is a lot of interelectronic repulsion in there. And in fact, this is something that one can calculate, this interelectronic repulsion in any family, but in particular in this one. So we use the Hubbard model. If we suppose we have a chain of hydrogen atoms, then they go to an excited state, just passing one electron from the top to the bottom. So this is the difference between the ionization energy and the electron affinity. This is again general chemistry, and I should perhaps apologize again. So by the Hubbard, we can get, in the case of hydrogen, this is about 12.8 electron volts. Now, this has been established before for the lanthanides, and a very interesting thing, well, here you go from lanthanum 3 to 4 and 2, so when you are adding or subtracting an electron. And in fact, the electron affinity gets eliminated. So it's the difference between the electronic ionization potentials. And this you can measure, for example, by photoelectron spectroscopy and inverse photoelectron spectroscopy. In the case of gadolinium, this is about 12, minus 8 and 4, 12 electron volts. Well, for the whole family of the rare earth metals, then we have this plot. And well, it's sure that you have seen that there is a relatively close relation between the one and the other. So we thought that perhaps the reason for the behavior in the synthesis process of these materials is due to the Hubbard, with the Hubbard model, to the intra-atomic electron repulsion. So this is an electron repulsion within the very atom, not the one atom with the other one. And so when we plot our representation with this, it correlates quite well. In fact, we have to go deeper into this correlation, and in the past it has been a lot of work on the lanthanides in the 50s and 60s, because at the time they had to separate the lanthanides one from the other, so they used the partition in different solvents, and there already they saw a change. You see, there are four sections here, and this was studied by, for example, but this is just the partition coefficient of a solid between two liquids. It's well known that if you have to extract a solid with a solvent, it's better to do that in parts than in one single time. You get more, and this is easily demonstrated thermodynamically. So, in fact, this is what's called the tetrad effect by Pepper. Jorgensen, one of the 100 Jorgensens, which is in the literature, nephelaucetic means cloud expansion. So, in fact, the interelectronic repulsion is cloud expansion. And then there were some calculations of this, and there are also some measurements. And then these are the data which are due to polarization of the spins and so on. In just a minute. And then it was also a previous work that the hydration of these lanthanide ions has a more or less similar situation. So, all in all, we published this in Inorganic Chemistry. You can see this is spin polarization due to the interelectronic repulsion, interatomic, the orbital polarization, and the spin orbit coupling. So, in fact, what we believe is that we observe this complete disruption of the lanthanic interaction in the synthesis of these materials for a phenomenon called intraatomic electronic repulsions that happens in the lanthanide, and this will be the conclusions of the first part. And this is really not the size which modifies the position or the structure or whatever, it's just the intraatomic interelectronic repulsion of the F orbitals. And apparently it's the first time that you see the influence of this intraatomic interelectronic repulsion in the kinetics of a chemical reaction, in this case in the solid state. So the next thing we'll go to the second, yes, we'll go to the, I think it's the second. Yes. Sorry for the stopping. Well, we have seen the influence of this interesting property in the synthesis. Now we are going to see a little bit more on the superconducting properties, and this will be in this similar family, but with molybdenum and copper, so replacing part of the copper of IPCO with molybdenum, or the ruthenium in the previous one by molybdenum and copper. And this is a very interesting family too. Well, this is well known. You know that in the superconducting plate you create holes and then they became superconducting. This is a conventional phase diagram. It has been shown here several times. I may come to the end. This is from Bosonic long ago. And there's the superconducting region. This is the optimum the hole concentration. Okay, so, well, you know that when in the underdoped region, and so you have different electronic phases in the non-superconducting area and so on and so forth. So now we are going to use a model of the IPCO, which was developed by Alario and his group, considering IPCO as a Josephson junction. So in fact, you have here, interbilayer, so that will be a bilayer, the two superconducting places intrabilayer. This is interbilayer in between the two superconducting places. And the crucial things for superconductivity in here, or at least one of the crucial ones, is the apical distance of this oxygen with respect to the planar and the superconducting plane. So, as according to Cavalieri and his group in Hamburg, you have here superconductor, insulator, superconductor. So this is a Josephson junction. And in fact, what happens here is that when you get connectivity, I mean, when electrons go from the one region to the other, you observe that this distance decreases, increases, this distance decreases, and the atomic, the apical distance decreases. So, in principle, that will be the idea of the transfer of charge from one place to the other. These experiments, which are extremely interesting in my view, is they have used light to excite IPCO, and they have arrived, it's by pulse laser pulses, and they have arrived to obtain instantaneously room temperature superconductivity in IPCO. You should go to his publications, which are very interesting. We haven't used light, we have used chemical substitution, as we'll see. So, if you look at the literature, then in IPCO, the cuprates, the critical temperature goes in parallel with the apical distance. So in IPCO, 230, 90, 243, 98, and so on. In the mercury, 280, 127. So there is an obvious relation between this apical distance and the TC. However, if you consider just one of these, not family with family, but one of these, the opposite happens. So in fact, in the case of IPCO, that when you have what I would be a similar approach, what happens when you increase the oxygen content is that, well, you get some atomic displacements, and as I say, the intra-bilayer, this double layer which is in the category model, this one normally increases, this one decreases, and that increases the transfer of charge, and then the apical distance decreases. So let's go to our materials, and then we found this work by 2 years ago of some of these materials were superconducting and some were not, depending on the size, which is planning on there. So in fact, if we put this was very old, in 1993. So it's interesting that here you have the thulium and ytterbium are superconducting, gadolinium also but at much lower temperature, and then the big ones are not superconducting. So we have an important example of size influencing temperature. Let's have a look inside that. So try to understand this. And our present work was just preparing this material. These are the characteristics of the rare earth atoms, big, small, and in the middle. And then, so these are the syntheses of the materials. They are rather easy to make. One second. And in this case, you don't really need high pressure, so you can make them. And now, the point I'm going to make is that you can use high-resolution microscopy to see in the atoms what happens in this process and why you are or not, you have or not superconductor. So we using the high microscopy, well, you can get the unit cell, the reciprocal unit cell and everything. That is the structure. This is in the case of thulium, and you see that it's a perfectly organized material, and this is a very simple thing in theory. Well, this was done in this electron microscopy center that I founded in the 80s, long ago, but these microscopes are more recent than theirs that I had. This is 200 kilovolts for high resolution electron microscopy. Like the previous picture I showed you, this is aberration corrected atomic resolution. So here we are in an order of magnitude deeper. So there are 2 ways to do this. One is annular bright field. So if this is the kind of, you use the diffracted spots in this ring around here, and then you can see there the anionic sublattice. So this is a very high resolution, atomic resolution electron micrograph, and sorry, suddenly I was shocked. So if I put here the details of the structure, well, this is the pyramids with CO5, so you can actually see the coppers and the oxygen. This will be the copper, this will be an oxygen, and in this is the charge reservoir layer, and you see that in the charge reservoir layer there are some positions which are not well occupied. It's very clear, here there is an oxygen, here there is very little, here there is nothing. So in the charge reservoir layer you have empty positions or oxygen vacancies, and they are disordered. So we have a disorder in the charge reservoir layer. Then, well, there are also other things in here which are interesting. For example, you can see that there is a displacement of the oxygen towards the neodymium. This is strontium, neodymium, strontium. So the oxygen go to the 3+, because they don't have at all enough positive charge. So there is also in these vacancies some displacements. I perhaps should not enter into too much detail, but the conclusion is that we have anion disorder in the charge reservoir layers. The second mode to do very high resolution, atomic resolution microscopy is to use the so-called high-angle annular dark field. This is a dark field image. Again, in this here, you use another type of electrons put in another kind of frame. So, without entering into detail, so we have these 2 images. One is for neodymium, the compound of neodymium is molybdenum, copper, neodymium, etc. And then we have two very high resolution images in dark field. And you see, well, this is the structure, this is the strontium, neodymium, strontium, these are the copper and the copper with or without oxygen. And you notice that they are clearly very different, these two images. In here, you have similar contrast between the strontium and the neodymium. The rare earth, neodymium, and the strontium, it's very similar contrast. Well, however, in the other one, where you have the thulium, there is a similar contrast. So, very well, it's a dissimilar contrast, similar and dissimilar. So here we have a dissimilar contrast, means that the atoms must be different. In here, where we have a similar contrast, the atoms are relatively similar, otherwise they will not give similar intensity. So in fact, that is the point. You can see here at the atomic level, but in the cationic sublattice, that you have disorder. But you have disorder in those whose size is similar to strontium, and not in those which are smaller. So this is why, as we are saying, this is what when you can also go along one of these lines and obtain the relative proportions of the different cations in the A position, and then we have the anti-side disorder in the A position for the big ones. So if we go back to this, we have anti-side disorder in the anionic position, in the anionic lattice, as we showed in the previous slide, and then in the A position. And this one you can also study by synchrotron, and then you see if you put no anti-side, you get a bad refinement, and then if you put anti-side in a certain proportion, you get a good fit. So in fact, the synchrotron data also confirm the existence of anti-side. So these are the results of the structural model, or the structural study rather. So what is happening, and this depends on the size of the rare earth relative to strontium, is that you have an exchange of this that originates the disorder. We then, these samples which were non-superconducting, we treated with ozone at moderate pressures, and they became superconducting, some of them, and some not. We go to that, and then just getting to the end. The copper oxidation state is in all cases higher than the optimal doping level, 2.16, which I mentioned before. And then the resistivity measurement, you can see that gadolinium and ytterbium and thulium are superconducting. Praseodymium and aluminum are not, and gadolinium is in an intermediate situation by its TC. So that in fact this is the praseodymium and aluminum non-superconducting because of the anti-side disorder and also the anion disorder in the lattice, and the others are superconductive. So there is a key role of the size in this case, and this key role shows in the temperature. The last experiment we've done is to use high oxygen pressure, and these are my two last slides. With high oxygen pressure in the unit cell press, putting potassium chloride, it decomposes and gives you oxygen at high pressure within the cell. And then we were able to go much higher in DC. So the maximum at high pressure of this is 83 Kelvin, which is again the maximum in the family. And well, this has the data concerning the TC and the oxidation state. And the interesting point, and with this I conclude, is that all these materials are in the overdoped side. And in fact, what happens is that, I mentioned that I haven't shown, but when you oxidize these things and modify the composition, you get a decrease on the apical distance, and then TC increases, you see. When you approach the superconducting plate, TC increases, and it increases quite a lot, to 83 Kelvin. So the phase diagram shows that here we have superconductivity very far from the usual composition, which has the maximum at 216. That doesn't mean that all the holes that we have participate of the superconduction. That will probably require another study. But what we like to show is that you can actually have superconductivity in important amounts in the overtoped region. And so with this, I finish. Oh, sorry. I would like to dedicate that to Professor Emilio Moran, who was my whole life working and died from COVID, and he was in the middle of this work, and this I always get emotional when I saw him. So this is the people that has been involved in the last part of the work, and this is the present group of my group. As you see, I'm in the back now, because I'm in the back seat of the Dakar. Thank you very much.
Thank you very much for such a wonderful lecture. And now it's open for any question or.
Yes, Miguel, thank you for this presentation. I would like just to make a comment about this last part, that in the molybdenum doped 1212, in fact, TC can be even higher, in 87 is the maximum, and also that it's not really the second dome, but it seems that the TC saturates. So I will speak more about this tomorrow, but
yeah,
it seems really that
I
there is
expected that.
Yeah. Okay, so I just wanted to make this comment.
Yeah, thank you. Yes. Yeah, well, we've been collaborating and working on the same thing for years. Yes.
I was a little bit surprised that you used the Hubbard U to parameterize this effect up-down, okay? And because you are in a situation where the orbitals, the F orbitals, are only weakly screening. And in that case, the attraction between the electron and the ion, the nucleus, is a much stronger effect than the interelectronic repulsion, generically speaking. So can you comment on that?
Well, I can comment saying that we look at that and we found this, and this fitted our model. So we just stop in there. Probably we should go deeper and see what is really the culprit. But well, this is a good approximation at least, but it's not probably the only truth. Yeah, I don't really know another model for that occasion, yes.
We know each other a long time, and you knew Alex Miller and other guys, and we were celebrating Alex. So you be Alex Miller now, you show us the direction. Where would you guess that we go? What do we tell to our students?
But
Which is a good candidate now for you?
yes,
So we can spend again another 20, 30 years,
yes,
but you've done a lot of work already.
yes. Well,
So if you have one candidate, tell us now. If not, we'll discuss over coffee. Thank you.
okay. And candidate, you mean?
Yeah, material.
Yes. Well, I will find one for you over coffee.
Okay, thank you.
Any other question or comment?
Yeah, thank you very much. So we do, in recent years, we developed a picture that we can measure the charges in the copper D and oxygen 2p orbitals.
Oh, the oxygen?
2p, the body orbitals. So we just sum up the charges, and it turns out that the TC across all the families is proportional to the total oxygen charge. So not the doped one, but the total. So maybe we can discuss this later. So there's a very empirical relation, and that brings you up to a TC of 300 Kelvin for oxygen charge of 0.7. So you need to go really to almost O1 minus in order to get the highest TC.
Yeah. Well, surely the total depends on the partials. So I attributed that to the partial, but probably the total gives a more general information. Yeah. Okay, we can, yeah.
Okay, is any other question or comment? Okay, so since we have the session starting soon, thank you very much again.